So welcome to the 37th Theoretical Physics Colloquium by Professor Yong-Liang from Hangzhou Institute of Advanced Studies at the University of Chinese Academy of Sciences in Hangzhou, China. He received his PhD degree in 2006 from the Institute of Theoretical Physics at the Chinese Academy of Sciences. He then had a postdoctoral scholar position between 2006 and 2008 at the Institute for Theoretical Physics at Tübingen University with Armand Fassler. He then was a research associate between 2008 and 2010 at the Institute for High Energy Physics at the Chinese Academy of Sciences. After that, he received an assistant professor position at Nagoya University in Japan, where he spent 4 years between 2010 and 2014. And since 2014, until this year, he was professor of physics and director of the Center for Theoretical Physics at Jilin University. Since 2018, he was also Vice Dean of the College of Physics. Since July 2020, this year, he is a professor of physics and Vice Dean of the School of Fundamental Physics and Mathematical Sciences at Hangzhou Institute for Advanced Studies of the University of the Chinese Academy of Sciences. His research interests are including many fundamental problems in particle and nuclear physics that includes the origin of the nucleon mass, medium modified hadron properties, patterns of the symmetry, breaking and restoration, effective theory methods, physics of complex stars, and many other topics. Today, he will be talking about topology change, emergent symmetry, and complex star matter. So you may start now.
Okay, so good morning, everyone. Actually, in China, it's midnight now. So thanks, Professor Igor, for your invitation, and thank you very much for your introduction. So it's my honor to have this opportunity to introduce our progress on the dense nuclear matter in the past past several years. So the title of my talk is, as you can see, Topology Change, Emergent Symmetries, and Complex Star Matter. So this actually this series of works was done with Professor Mankyu and Sakli and also other people from Nagoya and also from Korea and also from the United States. So this is an outline of my talk. So first I'll go a very brief introduction. Then I will introduce the first issue of our model based on topology. And after that, I will explain the second issue of our model, the so-called hidden symmetries of Qcd. So after these two issues or key points of our model, then I will construct our model for dense nuclear matter. After that, I will show you the predictions of our model, the so-called pseudo-conformal model. So finally, I will summarize. So what's the key point of the model? So let me start this talk using this slide. So I think this is it's well known in the nuclear physics society. So the equation of state of nuclear matter at high density is totally mass and uncharted domain. So you can see the symmetry energy at densities above normal nuclear matter density is very mass. So we don't know how to control it at this moment. We don't have any idea from lattice Qcd, or we don't have any constraint from low temperature terrestrial experiments. So anyway, at this moment, we don't know how to confirm this. It's well known that for finite nuclear as well as infinite nuclear matter can be fairly accurately accessed by using pionless or pion-full model. So we in our notation we call this SEFT. So based on the relevant symmetries and the invariances of along the line of Weinberger's Fock theorem. So the SEFT as befits their premise are expected to break down at some higher density. So like the density is relevant to interior of massive complex stars. So for example, in SEFT, the power counting in density is a formula momentum. So if you want to study the nuclear matter properties around saturation density, so we should already make the expansion around to fifth order. So it's a very the calculation is already very complicated. So the density much higher than this saturation density. So it's out of our control. So our strategy is to construct a generalized nuclear effective model which captures fully what the SEFT successfully done up to N0, and also can be extrapolated up to the density where this SEFT is presumed to break down. So anyway, we want to have an effective theoretical model which can be applied from low density to very high density relevant to compact stars. That's our purpose in the past several years. So to control our model, also to test our model, at this moment, we use some observations from astrophysics, like the observation of massive neutron stars here, and also the properties of nuclear matter or star properties extracted from this the recent gravitational wave detection. Yeah, and also this nuclear matter property, this pressure also extracted from this the constraint from the neutron star, or sorry, the gravitational wave detection. So anyway, we use these constraints to test our model. So the basic physics considered in our approach is as follows. So first, we consider the hidden topology in QCD. So hidden means it's not observed in matter free space. So we're using this topology property and the topology change, which I will define later, to incorporate the quark-hadron continuity in our approach. So rephrase using Chester's principle. So second point is in our model is the hidden symmetries of Qcd. So like the hidden scale symmetry and the hidden local flavor symmetry, and also this hidden parity doublet structure of nuclei. So this is the two key points we included in our model. So the model is like this. So our GnEFT equals, let me use this, I think this equation, the standard effective field theory of nuclei, including pion and nuclei, or baryon field, then plus rho and omega meson, which is very important to understand the nuclear force, and also the scalar meson, the lattice scalar meson, so which we need to get the attractive force between nuclei. So these two kinds of mesons, vector mesons and scalar mesons, are introduced using some symmetries of hidden symmetries of QCD, like rho and omega meson. We use the hidden local symmetry, and scalar meson we regard it as a dilaton or Nambu-Goldstone boson of hidden scale symmetry. So of course, both symmetries are intrinsic in QCD, but not visible in matter free space. That's why we say it is hidden. So we presume, of course, based on some theoretical analysis and arguments. So we presume these two symmetries are got unhidden by strong non-perturbative nuclear correlations, as nuclear matter is highly compressed. So then this emergent or unhidden of this local symmetry can be verified, or maybe verifying this Suzuki theorem, which I will show you later. This is a brief introduction. I will explain later a little bit more. And also this unhidden scale symmetry maybe indicate an IR fixed point with both chiral and scale symmetries realized in the Nambu-Goldstone mode. So these two symmetries. Then how the topology effect enters the system. So the topology or the quantitative conclusion obtained from the topology calculation enter the system through this Wilson match. First, for example, if you consider the process in effective theory, so this J is the external source. So after calculation, in this side, this correlation function can be expressed in terms of low energy constants. But if you want to make calculations, suppose we can do it. Then after calculation, this correlation function is expressed in terms of intrinsic QCD quantities, like Q bar, a vacuum solution of Q bar or G square gluon field. So this is in the sense of matching. So if the vacuum is modified by medium, so this quantities should depend on density. So that's why we regard the low energy constants in medium. If we want to apply the effective theory in medium, we also regard this low energy constants as a medium dependent quantity. So that's how the topology enters the calculation. So regard this density dependence as intrinsic density dependence. Yeah. So in the full calculation, we not only include this intrinsic density dependence, but also the induced density dependence, or this is not I. Induced density dependence arise from the nuclear correlation, and also the which also violates the Lorentz invariance. So the full density dependence equals these two parts. So then our model construction is based on the effective theory. So written in terms of the standard hadron degrees of freedom, like pion, vector mesons, and also nucleons here. And also this chi is the dilaton field. So this part accounts for the scalar symmetry breaking. This is the full Lagrangian or effective model we are using. So anyway, I want to emphasize our model is constructed in terms of owning hadrons as degrees of freedom. So the intrinsic density dependence enters the system through the web of dilaton or the scalar symmetry, the web here. So information from topology change is considered by using the parameterization of the density dependence of the low energy constants. So nuclear mass stays as a constant after topology change. So this is based on the paradoxical structure, which also I will also explain later. So the topology change density in half. At this moment, we don't have any constraints. So we regard it as a free parameter in our calculation. Yeah. So the philosophy like this: the quantitative information from topology change enters the system through density dependence of low energy constants. So we will use the Chester's principle. The topology change can be explained as a hadron quark continuity. So that's why hadron quark continuity enters our system. So how the hadron quark continuity enters our system. Okay, so this is that's what I want to briefly introduce our model, the key points of our model. So let me explain a little bit details. So the topology, so it's well known. The in large NC limits, barons can be studied, or it's reasonable to regard baron as a soliton or skyrmion based on the skyrm model. So if we want to put the skyrm or skyrmion to the crystal lattice, like here, so then we can use this system to study skyrmion matter or nuclear matter. If you believe skyrmion is a nucleon. So then in this sense, baronic matter, baronic interaction in full regions of density, so up to relevant causal complex stars, can be accessed using this approach. You just need to squeeze the size of the crystal. Then the density could enter the system. So an interesting observation in this calculation is as follows. Supposing you choose a face-centered cubic crystal, if you look at the distribution of number density along axis, so this blue area is the distribution of the baryon number density. So then it's like this. If you choose one cubic crystal, if you choose one crystal seal, like this, when the crystal size is big enough, so it's like this. If you choose face-centered cubic crystal, so when the number is 1, if you integrate around this region. So if you suppress this system, people found after a certain density, of course, the location of density depends on model. So let's look at this line. So this different line corresponds to different models. Forget it. Let's look at this. So people find after the critical density, the distribution of baryon number got changed to this form. So this blue square is the crystal, the size of a crystal seal, and this blue square corresponds to original crystal seal, the size of crystal seal. You find, so in addition to the original vortices, like here, and here, like here, there are also baryon number density appear at in the middle of the line connecting these 2 points. So based on symmetry analysis, people find if you integrate over this region, the Wendy number in this region is a half. So this here is 1, here is 1/2. So this means there's a this Wendy number topology quantity is 1. This is a half. So regard this as a topology transition from Wendy number 1 of system to Wendy number half system. So how to characterize this change? It is characterized by the quark condensate. So on space, in this system, people find after this change from low density to high density, or from this big crystal size to from this big crystal size to small crystal size, the space average of QQ bar becomes 0 at this side. Although locally it's not 0. Then this plot gives you an idea. So the crystal size dependence of this QQ bar, space average QQ bar. So this arrow is the crystal size. This is the volume. Give this. Yeah. So this means, in the sense of space average, quark condensate vanishes. However, after this topology change, the nuclear mass or soliton mass is not 0. So you can see this side is not 0. So it means nuclear mass is non-zero. So in the sense of space average, people find the nuclear mass is not solely from carrier symmetry breaking. So it includes a carrier inverted mass. So this supports the parity W structure people used in hadron physics. So actually, this behavior is also supported by some analysis using parity W structure based on the model of parity W structure. So yeah, then that is the prediction. Then what is the prediction of symmetry energy? So if you want to calculate symmetry energy using the crystal system, you should collectively rotate the crystal. So after that, if you regard the soliton in the system is a pure neutral matter. So before and after rotation, before rotation is soliton without quantum number. But after rotation, we regard the system as a pure neutron matter. You can extract the symmetry energy by differentiate the energy of a system. You can obtain the symmetry energy of a system is proportional to the inverse of the momentum inertia of one crystal of the soliton in the crystal. So this is expression. So what you need to calculate is simply the momentum inertia in the system. So people found the symmetry energy first decrease as density. This what is density from small to high. So first decrease, then after the topology change, symmetry energy got increased. So this behavior, let me see, this quantitative behavior is model independent. How to say model independent means we checked several models. So this quantitative behavior is independent of the model we choose, like a pi model, or pi model, or pi rho model, or pi omega model. So we check this. And if you combine this quantitative behavior with nuclear correlation, so the symmetry energy in this, based on this idea, should be should have this behavior. So this is if this is right, anyway, in that case, it means this decreasing behavior is not does not agree with this behavior. So if you believe this, or if you think this is right, so some part of this symmetry energy behavior could be excluded. So this cusp structure is associated with the topology change with the emergent of quasi-particle structure with half skyrmions. So this is locked to this. So, okay, let me skip this. I think, yeah. Then, how to answer? What is the meaning of the topology change? So, if you look at this, if you go to the Chesa-Cat principle based on the Carroll-Beck model, this topology change may be regarded, can be regarded as hadron to quark continuity. So let's consider a Carroll-Beck like this. Inside the bag, I think you're familiar with this. Inside the bag, there's a quark. Outside is meson cloud. So this explains the barrel number communicated between the inside bag and outside bag through the boundary condition. So outside is outside the bag, there's only meson, and the meson carries topology charge. So in this whole system, the baron charge is is divided into two parts, inside part and outside part. To make some calculation. If you sum up these two, you get baron number in the system is 1. Total is 1. But what's the magnitude inside the bag, outside bag, depends on the bag size. Then let me look at the example for the proton case. So people calculated this Fleetwood singlet axial charge before using this picture. So people found this charge Ga is, let me say, this part is the contribution from the quarks and the gluons summing over the quarks, and this part is from the gluons inside the. This part is from the quark inside, and this part is from the topology outside. So then the total contribution is sum of these two. So this black line is the total contribution. So this axis corresponds to the size of the bag. So when the size is very small, the size when the bag is very small. So it corresponds to the physics carried only by topology. So when the bag size is big, it's like this picture. It's carried by the quark enters the system. So then, but the physics is independent of this this bag size. Yeah. So this gives you the idea, the Chesa-Cat principle. So the physics is independent of the the face of the cat. So no matter cat is here or not, the physics is the same. Sorry, let me skip this. Then that's the topology in our system. Then let's see the hidden symmetries of the system calculate. We will consider. First is the hidden local flavor symmetry. This is the redundancy in the decomposition of the pion field. If you make this redundant, you divide U field in this form, you can sandwich a unitary matrix, and the unitary matrix is a product of gauge transformation and its conjugation. So if we make this as a gauge field, you can introduce gauge field to the system. Then after symmetry breaking, they get mass. So this gives you the symmetry broken gauge field can be regarded as the vector mesons in the system. Yeah, this idea is totally different from one could call standard in nuclear community. Is that rho and omega is a hidden gauge field. So this is developed by Nagoya group. Now this model captures extremely well certain strong interaction dynamics even at tree level. So there's a theorem which we call the Suzuki theorem support this or related to the hidden gauge symmetry. So it says when a gauge invariant local field is written in terms of matter fields alone, a composite gauge boson or boson must be formally formed dynamically. So this means if this theorem holds for rho meson, if there's a massless rho meson at some parameter space, so then in that sense it can be looked at as a composite gauge boson. So the HRS with the redundancy evaluated to gauge field treated a Wilsonian randomization group, so has a fixed point at 0 equal to 0. This is discussed in this paper. So the KS-IF relation, the rho meson mass proportional to F pi and 0 holds to all orders. Hence, at the fixed point 0 equal to 0, the vector manifestation point there emerge a gauge field. This becomes 0. So the gauge field emerges. So based on this consideration, we use the proposition. So we think we regard hidden local symmetry can emerge in nuclear dynamics with the vector meson mass driven to 0 as the vector manifestation fixed point by high density. So this is how the hidden flavor symmetry emerges in our system. Then the next symmetry is the hidden scale symmetry. Let me skip this side. So how to include the lightest scalar meson in the nuclear calculation is not so easy. So in this paper, people based on some analysis or similarity between the mass of F0 and also K mass discussed in the chiral perturbation theory. So they regarded F0 as a pseudo Nambu-Goldstone boson, arisen from a certain some symmetry breaking. So after analysis, they find this symmetry is reasonable to regard this symmetry as the scale symmetry. So then they make this assumption. So there's a non-perturbative RR fixed point in the running QCD coupling constants. So the explicit breaking of scale inversions, they suppose there's an IR fixed point, non-perturbative IR fixed point. And also we are living slightly away from this IR fixed point. So departures of IR, departures of IFS from R fixed point plus quark mass gives the explicit breaking of scale invariance. So this explicit breaking of scale invariance triggers the spontaneous symmetry breaking, gives the pseudo Nambu-Goldstone boson, which can be regarded as F0. So because in that sense, how heavy is this F0 depends on the distance between our world and this R fixed point, this supposed R fixed point. So it's reasonable to regard this F0 as a Nambu-Goldstone boson, like a pion or kaon, which the mass depends on the magnitude of explicit Carroll symmetry breaking. So if this picture is right, this gives an approach to include scalar meson in Carroll perturbation theory. So you can to construct the theory, you simply need to write down the scale invariant part plus scale symmetry breaking part. This beta prime is the first. This is the derivative of beta function of QCD, which breaks the scale symmetry. So this is straightforward. Okay. Okay. Now let me discuss how the paradoxical structure model by using a Carroll effective model. How the Carroll invariant mass arise in the Carroll effective model. So this model is so-called. We start from the paradoxical structure. So this is the paradoxical structure, and this chi is Carroll invariant part. This is dilaton field. So this is written in the non-linearization of Carroll symmetry. So it means Carroll symmetry is already broken. So if we suppose there's a medium induced or put this make this system to the Carroll symmetry restore the phase, then people find in that case, in this case, nuclear mass, negative or parity nuclear mass is written in terms of this. When this S is the vacuum expectation value of the sigma part. This sigma is dependent by combination of chi and U field. You reparameterize it's here. The sigma is U times chi. The chi dilaton, U is the Carroll field, the dilaton field. You can write this in terms of this this form. This S is the value of S is here. So people find if we want to get this get this S Carroll symmetry restored phase, this S should go to the 0. But if you write this system, rewrite this using this notation, using this sigma, you can find S should be in the denominator of the appears in the denominator of some combination. So if this system is regular, I mean not singular, that numerator of the parameter should be 0 also. Otherwise, this theory becomes singular. In that case, people find this behavior. This like this V rho goes to GA. GA is parameter GA is here. This is axial coupling. And also combination of parameter alpha. Alpha is F pi over F chi. F chi dilaton, the constant of dilaton should goes to 1, and the ratio should goes to 1. And also nuclear mass, the negative parity and positive parity nuclear mass becomes degenerate, goes to M0. So this gives the Carroll invariant mass. And also rho n coupling goes to 0. So rho decouples from the system. In that case, using this system goes to the linearization of Carroll symmetry. So based on this observation, we propose we make a proposition So when moving toward to the dilaton limit fixed point, the fundamental constant is in scale chiral symmetry get transformed as f pi goes to f chi. So GA goes to GV rho goes to 1. And the rho meson decouples while the omega remains coupled. So here is we only constraint the non-abelian part of the hidden symmetry. For the U1 part, we don't have any control in this analysis. So this breaks the Flavor U2 symmetry. So that's the definition of a dilaton limit fixed point. So the emergent of the behavior of a nuclear mass can also be obtained based on the mean field calculation, including dilaton field. So because there's a interplay between omega uncoupling and also the value of chi to make the coupled equation in the mean field calculation. People find if omega meson behavior coupling constant of omega meson behave like this, you can also get the value of chi behaves a constant of the certain density. So if you look at this, calculate the energy momentum tensor of this system, or calculate the trace, you can find the trace of energy momentum of the system only depends on the dilaton field. So this gives you the chi, and then it means the value of chi in medium goes to constant, means this trace of energy momentum goes to constant. Now let me come back to this slide. We combine the behavior, the quantitative behavior from topology change, and also from the expectation from the hidden symmetries in QCD. Combine this information to the effective Lagrangian, including Olin hadron field. We construct the model. So how to construct the model is like this. We have found before and after topology change, the hadron properties have different behaviors. Yeah, like before after topology change, we parameterize this behavior using a scaling function. Then we use this scaling function to the theory, embedded to this theory, the only constant in this theory. It means intrinsic density dependence enters the calculation. Then we make the calculation using the V low k, which means hadron fluctuation is included in the system. This means beyond the mean field calculation, using this step, based on in this step, the induced density dependence also enters the system. Then using this calculation, we construct the equation of state of nuclear matter with both IDD and DD induced. Yeah. So this is how our calculation, how our model constructed. So this is the point is the calculation using V low k, and this line is the fate of V low k. We find this calculation, V low k calculation can be parameterized or fitted using these two simple functions. So this function of high density is pseudo-conformal prediction. So like the power is 1/3 and -1 based on the conformal equation, and also the fate of this symmetry energy. So this is our model fit of the nuclear matter property around the saturation density, are slightly higher, 2 and 0. So you can find this prediction predictions agree with the empirical values quite well. So it means this model at the low density is believable. And an interesting prediction of the model is that the trace of the sound velocity after topology change approach to this conformal constraints, although the trace of energy momentum tensor in this sum is not 0. So this is because, as I said, trace of energy momentum is a density independent quantity. So this appearance of conformal sound velocity is logged to the position of topology change. Yeah. This you can see this appearance of the sound velocity, the density not so high. This feature is not shared by any other models or theories in the field. So normally, this is a standard scenario of the sound velocity in the society. So normally it appears at a very high density where PQCD is applicable. Our calculation is different from this. So this is the calculation of the prediction of the model. This is why our model is so conformal. Conformal means sound velocity satisfies the conformal constraint, but pseudo means this trace of momentum tensor is not zero, so it's not a real conformal. So we regard it as pseudo conformal. So this is a prediction of star properties, and you can see this is higher than 2 solar mass. 2 solar mass agreed with the constraint of observation of astrophysics, accommodate massive star. And this is the symmetry energy. These dots are from this paper, which is extracted from the astrophysics. So also our prediction calculation in the region of the fit, and also this is the pressure as a function of density calculated in our model. So this also from this paper extracted from the astrophysics. So this gives us first conclusion: position of topology change is constrained to 2, 4, and 0. So 4, in case of if it is bigger than 4, this is beyond the constraint of astrophysics observation. It cannot be small because topology change means the half-binding number object or half-barren number object appears. So this is if it is too slow, it disagrees with our nature. So it cannot be so small. So this is the prediction of the Tudor deformability of this combined system. So this is the band of the slow rotated star. So you can see this somehow agrees with the when n half equal to 3, 0. This agrees with this constraint below. And this is the extracted from the constraint extracted from the GW observation. This line contour gives the constraint at 90% confidence level. So below this satisfies this. So this is our prediction. So it's okay. Another recent observation is our prediction is that people recently found make a comprehensive analysis of the equatorial state in the market. People found states. So the smallest density from which this polytropic index gamma is continually less than 1.75 to asymptotic densities is identified with the onset of quark matter. In this paper, people regard this. And then based on this, they conclude in the massive neutron stars, there should exist of cores made of quarks. So this is a standard scenario, not an exotic or native. But we recently calculated these quantities. This sound velocity I showed you before, and this is the polytropic index. Polytropic index. We find in our model after topology change, polytropic index is smaller, could be smaller than 1.75, and actually approach to 1. But as I said before, after topology change, our matter is still made of in our matter, chiral symmetry is not restored, and the nuclear is still nuclear. So it means there's no perturbative quark in the calculation. So anyway, this calculation tells us from if we build our model, we do not agree with this calculation. So this is the This is a comparison of our equation of states with that extracted in this paper. This red line is our prediction. This blue green area is that constraint from the conformal matter. So you can see this line is nearly parallel to this band, but there's distance. The distance is constant. That's why this nearly this nearly constant distance accounts for the deviation from the true conformal constraint. And recently, to see more how to pin down or how to pin down the topology change, we using this model calculated the GW gravitational waves emitted from neutral star merger. So this make a calculation. We found the topology change. This is the 1.5 solar mass to 1.5 solar mass merger. We found that when the topology change, we choose two position topology change, 2n0, 3n0. We find this wave shape, this GW waveforms is different, and also this difference is within the ability of the ground-based GW detection facility. This gives the idea of why there's a difference. Let me skip this because this difference accounts for the stiffness of the equation state, because it says how easy the exchange of matter in this system. Yeah. So if people in the future GW detection can pin down or make precise measurements, the GW, probably we can see something about the location of topology change. So let me summarize our model. So our pseudo-conformal model for dense nuclear matter considered hidden topology and plus hidden symmetries in QCD, and quark hadron continuity enters through the topology in the sense of Chester's principle. And since in this system, the trace of energy momentum tensor is non-zero, although its sound velocity satisfies the conformal constraints. So that's why we see this model is pseudo-conformal. And at the low energy region, below 2n0, this model stands for the test from both nuclear physics and also high density, stands for the test from both nuclear physics and astrophysics. For example, it accommodates neutron star up to 2.23 solar mass at this moment. So in summary, at this moment, we don't find anything at odds with nature from this model. And at this moment, the constraint of the topology change, the position of topology change is 2 to 4 and 0. So thank you so much. That's all.
Thank you very much for presentation. Let's go to questions now. If there are any questions from the audience, please let me know. Any questions? Okay, let me start with a question that I had first. So when you're constructing the equation of state within this framework, you seem to have at least one free parameter to choose and 1/2. Do you have any other parameters? So how flexible is your equation of state? Which other free parameters do you have, and how the equation of state could change with modifying all of them?
Okay, that's a good question related to details of the model. So at this moment, when we include the quantitative behavior from topology change, we should parameterize it using the scaling function, density dependence of function, phi1, phi2, I mean 2 regions. So we only use the quantitative behavior. So it means we don't have any definite function form. of this scaling behavior. So what we have is from low density to up to n½ it decrease like f pi mn. So after that it becomes a constant. So we should choose the function form, the function of this scaling behavior. But once it is once these forms are chosen, so everything is fixed except n½ this n½.
But these functions, f1, f2, they can be chosen in very many different ways, I assume, right?
Yes,
so
yes.
that would affect the equation of state.
Yes, but let me say, it's at high density, we should pin down the two functions at the n½. So it means that if the function form at below n½ is fixed at high then the function form at above n½ is fixed. Then the function form at low density is constrained by this. It's already a very strong constraint.
Okay.
Yeah.
I see. Okay, so the low density kind of fixes everything.
Yeah.
Okay, next question, Rob Pisarski. Go ahead.
Hello, sir. Very pleased to meet you.
Yes.
I don't think we've met, but I very much enjoyed your work and I very carefully followed it.
Thank you.
I had several questions and comments. First of all, I wanted to say when you said at the beginning that the equation of state at high density is a total mess. I thought that was.
Yes, I follow this slide. Yes.
But I had more detailed questions. What is the shift in the omega mass at saturation density in your model?
Sorry.
The shift in the omega mass.
Oh, omega mass, the shift of omega mass.
At saturation density.
Sorry,
At saturation density.
let me reduce about at saturation is reduced about 20%, 15 to 20%.
Rob, did you hear that? I muted you briefly. Unmute yourself, please. Rob, unmute yourself, please.
Sorry. How does that agree with the results of the Sibelsa-TAPS experiment, which found no significant shift at saturation density, although the width went up by a factor of 30? This was from about 12 years ago.
Sorry, omega mass, the shift of omega mass is less than 30%, right?
Yeah, but I thought the limits from the Sibelsa-TAPS experiment were ruled out any such shift.
I remember there's a constraint from like rho to e plus e minus or phi to e plus e minus is around 10% to 15%. But for omega mass, I don't remember. I'm sorry, I don't remember.
No, it was a beautiful. They first claimed there was a shift, but anyway, let me go on. I have several other questions. So if Igor, you're welcome to interrupt.
Go ahead.
You said that your half skyrmion crystal had a chiral density wave, where you go to this
Yes.
N1/2.
Yeah, I did not show the slide, but yes.
Yeah. Have you checked the stability of that phase by looking at small fluctuations?
They check the
Stability.
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 Yeah.
Stability. Stability. Sorry, I cannot get the point. What do you mean? In the calculation, I don't know what do you mean stability. I'm sorry.
Yeah, okay, it's very simple. You have some non-trivial solution.
Yes.
You look at small fluctuations. You look at the second order fluctuate, to fluctuations to second order, you get an inverse matrix. And are the eigenvalues of that matrix all positive definite? That's all I mean. The reason why I mention it's not just a perverse question. It's because in recent work with Alexei Svelek and Semyon Valgushev, we showed that in a related model, with an O4 model, that the chiral density wave for a special solution where you have a single Fourier mode is destabilized and forms what we call a pion quantum spin liquid. So I just wanted to ask, we could only check for this one special solution, so I'd be very interested to know what's true for your solution. It should be straightforward to check. It's not trivial, but it should be straightforward. It's basically because you get a double pole at non-zero momentum, but I don't want to belabor that. I can. What I mainly wanted to ask you is on slide 32, you said we are disagreeing, and could you elaborate on precisely what you're disagreeing with whom? That was a little quick for me.
I think I cannot. I'm sorry. I think I cannot catch up the point. So that's,
Yeah, no, I'll send you an email. Could you please go to slide 32?
Oh, 32.
Yeah. You said we are disagreeing. I just wanted to know what you're disagreeing about.
Okay.
I think it was 32. Yeah, right there.
Disagree means. Oh, sorry.
Where you said we are disagreeing.
Disagree means, the standards. What I want to mean is that in the standard scenario, normally people think this conformal velocity appears at a very high density, around 50, or about 50, something like that. Yeah. In our model, we found this sound velocity appears like this around this region. So this is different.
Oh, so that's what you mean.
Yes.
Could you show me a plot of your speed of sound again versus density?
Yes, I think this is the slide. Yes.
Yeah, that's the speed of sound. I just wanted to ask you about this recent work by in October by Drischler, Hahn, Latimer, Prakash Reddy, and Zhao, in which they claim you had to have a very strong spike in the speed of sound at 1.5 to 1.8 times nuclear matter density. It's about where you have your spike, but I don't think it's as big as what they claim. I don't know if you have a comment on that work.
Oh, sorry, I did not realize that that paper. I'm sorry.
Okay. No, that's fine.
Yeah,
okay, unless Igor, I don't want to be rude, but I have one last question. If I
Go
can.
ahead with your last question. I don't see any other raised hands so far, at least.
Yeah. You referred to it with your skyrmion crystal topology change in quark hadron continuity. And I just wanted to ask you, there was work done by Alexei Cherman, Srimoyi Sen, and Larry Yaffe, who argued that because of the presence of Z3 vortices for 3 flavors and 3 colors, that there was a non-local way of distinguishing between the hadronic and deconfined phases, and they argued that you had to have at least one phase transition separating the two. Whereas you kept stressing quark hadron continuity, and their paper very clearly argues, and it may be wrong, but that's what they argue, that there is no quark hadron continuity. Okay, no, I was just wondering. It's a detailed.
Well, that was also a topological argument, in fact.
Yep. But it was very different, right? Because it's the rotation around. Who spoke about? Didn't Alexei speak about
Alexei spoke about that in this colloquium series, indeed, maybe a couple of months ago.
Yeah, I think I should read anyway. I think I should read this paper at this moment. Let me say, let me. In our model construction, we as I said, emphasized, we only use this quantitative behavior of like this to input this calculation into our model construction. That's what we use. Probably I did not studied very much about this mathematical side of the that field. So I cannot give.
No, I was just asking. Okay. Igor, I have one last question, but it's somewhat personal. So perhaps sir, if you could just hang on, and then Igor, if
Yeah,
you wanted to
you could
close
ask it after I'll stop recording.
Yeah,
Actually,
I just wanted to ask him not to hang
very
up.
happy to have comments about this model or something.
Yeah.
Okay.
But
Are there
certainly
any
agree
other
with the
questions?
parity doubling. Sorry.
Go ahead. You said something.
Yeah, I just wanted to say you're emphasizing the parity doubling. I strongly agree with, and I think that's very necessary.
Okay.
Please.
Okay. Other people in the audience, are there any other questions before we wrap up the official part? I don't see any other questions, so I would like to use this opportunity to thank the speaker once again. Thanks for a nice presentation. I really appreciate you doing it on such a short notice.
Oh, thank you very much. Yeah,